Number 33 concerns the differential expression of linearity. And this is really very simple. If y is linear, then the average rate at which y changes, delta y over delta t, is constant. A linear function has a constant rate of change. Now dy over dt is what we use for the limiting value of delta y over delta t. That is, as we take smaller and smaller slope triangles, we get a limiting value, and that's what we call dy over dt. Clearly, delta y over delta t is always the same, so it doesn't matter how small we take the triangle. It's still going to be dy. We're still going to get the same thing. So dy over dt is just going to be equal to delta y over delta t, which is constant. So we say that the approximation here is dy over dt is constant. And that's how we characterize a linear function. Numbers 34 and 35 concern proportionalities, specifically geometric proportionalities involved with squares and cubes and areas and volumes. If x is the length of a side of a square, then the area of the square is a equals x squared, obviously. If x is any linear measure, for example the diagonal or the perimeter, then a equals kx squared. Okay, and this holds for any geometrically similar figures. It could be two circles, where x stands for the radii of the circle. X is the radius of a circle, then the area is proportional to the square of the radius. If x is the circumference or the diameter, anything that can be measured with a tape measure, we're going to have this proportionality. And this follows, and we're not going to go through the details here, it just follows from the fact that since the area of squares, the areas of squares are proportional to the square of linear dimensions, since any surface can be very nearly covered with tiny square tiles, as nearly as we like by making the tiles small enough, then the area of any geometric surface is going to have this sort of proportionality. Again, among geometrically similar figures, because when we blow up, expand geometrically similar figures, the little tiny tiles will expand accordingly. Similarly, for a cube, this horrible looking V stands for volume. We have volume equals x cubed. And if x is any linear measure, then the volume is proportional to x cubed. Volume is kx cubed. This is for geometrically similar objects. And just as any surface can be covered, or very nearly covered, with tiny square tiles as nearly as we like, any volume can be filled with little tiny cubes as closely as we wish. So that similar statements can be made. So that for all geometrically similar, for any class of geometrically similar figures, the volume is going to be proportional to the cube of whatever linear dimension we want to use.